what was on the answer key, then you need to do what's on the answer key. Because there were problems where there are like 15 arrows coming off of BR minus. And it's like, no, no, no. So you got to show it step by step. So I will give you, I'll quickly go through those today, and then I'll try and scan them in and send them to you. But I will be in over the weekend, at least in the afternoon I'll guarantee from like 12 to 5 or 6, whenever. If the door's open, I'm there. If there's a little card on the door saying I'll be back in a few minutes, I'll be back in a few minutes. Whatever that is. It won't be very long. If not, then I'll probably be walking around the second floor trying to get my maximum number of steps in. So if you see me, you can yell at me, and if I hear you with my noise student canceling headphones, then. Okay. But if you have questions, put them up on Piazza. I will send out my sort of list of topics. Although I think the list of topics that people put online, there were 2 different ones, were very good. But I do have a list of topics listing reactions and things that I will put online as well today, once I find them on my computer. Okay, so questions.
Can you go over the 1, 2, and 1, 4 addition mechanisms?
The 1, 2, and 1, 4 addition mechanisms, yes. So, when you're looking at 1, 2, and 1, 4, and this was the one from the answer, or from the quiz that I just handed back, I think. So when you're looking at 1, 2, and 1, 4, you're always going to add an electrophile first. That electrophile would either be an H plus or Br2. So it'd be H plus and then either Cl minus or H plus and water. So we're always going to identify the 4 carbons in the diene system. So there's always going to be carbon 1, 2, 3, and 4. And that molecule is always going to be symmetrical. Okay? If it was unsymmetrical, then the problem is that you could add from either end, which means you're going to get 4 products instead of just the 1, 2, and 1, 4, because you get 1, 2 from one end. I'm not going to, remember, this is an easy organic class. I'm not going to make it that complicated for you to have to choose which one or write all of them. So it will be symmetrical. And so it won't matter whether I write 1, 2, or 1 to 4 from left to right or right to left. So you first show the arrow that goes to the positive charge. So you either show the arrow that goes to the H plus, like that, or if it's Br2, then what you would do is show the arrow that goes to the Br, and then the pair of electrons goes to the Br minus. So you're going to start your reaction out either way. And if we're doing Br2, we're just going to treat the Br2 as a Br plus. Okay, we're not going to have any bromonium ion or anything like that. We're just going to add Br plus like H plus. Okay, so any preference in terms of which one you want to carry through here? H plus, Cl minus, H plus H2O, Br2, Br2. Okay, so if we do the Br2, then I'm going to add a Br to carbon 1. That will put a positive charge on carbon 2. Okay. You can erase that Br and put an H if you'd like. But again, that's carbon 1, 2, 3, and 4. Now, you have to be careful here, because where people are likely to make a mistake is that you put your Br basically you put your Br at the where carbon 1 should be. Br1 has to be attached to carbon 1. That usually happens over here on carbon 4, and you may see that in your problems. You may, just to put a chlorine over here, you got to make sure you put the bond there. Okay, so then we form our secondary carbocation, secondary allylic. We're going to take this pair of electrons, move it here, so that then we form the double bond between carbon 2 and 3 and put the plus charge on the end. Then the Br minus is going to come in and add to each of the two carbocations. So Br minus adds to this carbocation, Br minus adds to this carbocation, so that the 1,2 product is formed, and the 1,4 product is formed. Okay, this bond to the Br off of carbon 4, that's the one where sometimes people will forget to put that bond and just put the Br there. You want to make sure you show the bond to the carbon 4. So then we only have 3 more things to do. We have to write the resonance hybrid, kinetic, and thermodynamic. So the resonance hybrid, what you want to do there is just write the structure without the double bonds and charges. So again, we've got a Br attached to carbon 1, and then we've got all the single bonds. In the 2 resonance structures where there was a positive charge, there now is a delta positive charge. And in these kinds of molecules, if you're into pattern recognition, the dotted lines go between the 2 delta positive charges. Or if you don't like that, then you just average out the charges. So single bond, single bond, single bond, double bond, partial double bond, single bond, partial double bond. So that's my resonance hybrid. Then, which is the most stable carbocation? The tertiary one. What is the most stable alkene? The one that has the 4 groups attached to it. So we choose from the intermediate which one is more stable. We choose from the product which one is more stable. The more stable intermediate gives you the kinetic product. The more stable product is the thermodynamic. So in this case, this would be our kinetic product, and this would be our thermodynamic product. Okay, that's how we would do a 1,2, 1,4. So whether it's in a ring or whether it's not in a ring, you're identifying carbons 1, 2, 3, and 4 in the double bond in the diene system. And then you're adding an electrophile to carbon 1, then the nucleophile to carbon 2, and then the carbon 4. But when you add it to 4, what happens? The double bond moves between 2 and 3. What else?
Can you go over the BR2 like radical stuff? Determination on the practical.
Of the BR2. What am I adding BR2 to?
It was like you had the radical and then you had it was like the initiation, propagation, and termination.
Oh, for free radical halogenation?
Yeah.
That was from last year's exam?
Yeah.
Remember, we did that first semester,
So it's not gonna be on
so it's not going to be on this exam. So we won't have free radical halogenation on this exam.
Will there be one where like we have to, I forget how it goes, but like we end up adding or like making the peroxide?
Yes,
We do one of those.
sure. So that's the peroxide formation by reacting the O2 with the ether is that's the only free radical mechanism that we have for this exam. Because the free radical that we did, so last year I held off in first semester doing free radical halogenation and we did it. So they had chapters 13, 14, 15, and then they had 18 and 19, and we skipped right to 19 because everybody allegedly did free radical halogenation first semester. That's why it's not on this exam. So what we do is we have oxygen. Remember, you have to remember that oxygen is in its diradical form. And so what it's going to do is it's going to abstract the hydrogen from one of the carbons attached to the oxygen. So I use half arrows to show basically breaking the CH bond. And then one of the arrows will go back to the carbon with one electron. The one electron in the CH bond will be used to pair up with the one electron in with the oxygen. So step number one is to form basically a hydroperoxide. So one end of the oxygen gets the hydrogen atom, the other end stays as a radical. And now I just couple those two radicals together. So I'm going to take this and this radical with half arrows and couple them together to form the peroxide. So as far as free radical mechanisms go, that's one's pretty short.
On the other side.
Well, so what I did was when I wrote this, I kind of took this one and I just rotated 180 degrees.
No. The one, if you go back to the first.
Oh,
You had H's on both sides.
they're still there. So this one's only 3 steps, and there aren't any termination steps or anything like that. As far as going back and saying, let's write the, entire mechanism for free radical halogenation, that would be if I invoked the rule that all the tests are completely comprehensive throughout the entire year. But if I'm going to do that, then let's do some RS problems. Let's do some, SN1, SN. Oh wait, we're already doing SN1 and SN2 with the ethers. So making the ethers. So there's a certain limit at which the comprehensive nature is. So that it was just last year we did free radical in the second semester, not the first semester.
Can we do some practice with the aromatics?
Aromatics, anti-aromatic, and non-aromatic. Okay, so
oxygen allowed to have, sp2?
No, it's not. You can only have one. That's true, that would violate the octet rule. Minus 20. Okay, so your choice is aromatic, anti-aromatic, or non-aromatic. So what about the first one here with the nitrogen in the ring? Criteria number 1. Are all the atoms in the ring sp2 hybridized? In the first one. Are there any that could be sp2 but also could be sp3? The nitrogen. So the nitrogen, any atom with a lone pair here, might end up being sp2 or sp3. So in this case, in order for this to be aromatic, the nitrogen has to be sp2. So that's criteria number 1. Is it going to be sp2 or not? So let's count up the total number of pi electrons and see how many we have. So right now we have 2, 4, 6, 8. What happens if the nitrogen becomes sp2? It now takes its lone pair and throws it into that pi electrons. So if the nitrogen becomes sp2, this lone pair automatically becomes part of the pi system. And if it automatically becomes part of the pi system, how many pi electrons do I have? I've got 10. Is 10 allowed under Huckel's rule? Yes. So that nitrogen is going to become sp2, and it is going to take its lone pairs and throw it into the pi system to make the molecule really stable and make it aromatic. So in this case, that molecule would be aromatic. Okay. If there were only something like, well, the only way that the nitrogen or the lone pair will go sp2 is if the pair of electrons will make the system aromatic. If it doesn't matter, if it won't make the system aromatic, or if it would make the system anti-aromatic, it's not going to become sp2. It's just going to stay sp3, and the system will be non-aromatic. Okay. So those atoms will never become sp2 to make the system anti-aromatic because it will not do something to make the molecule really unstable. Okay. So that one is aromatic. How about the oxygen 6-membered ring? What about the next one? Is this aromatic, anti, or not? Non? Aromatic? So what are the hybridizations of all the ring atoms right now without that illegal lone pair? Is the oxygen sp2? Can be.
We're not allowed to include lone pairs as molecules.
Depends. So is this oxygen sp2 hybridized? What?
Thought it was.
Is it? It's not could be. It is. How do we know that it's sp2 hybridized? It has 3 hybrid orbitals. We count hybrid orbitals by number of single bonds plus the number of lone pairs. So in this case, this oxygen has 1, 2 single bonds and a lone pair, So it is automatically sp2. Doesn't have a choice. It's automatically sp2. So criteria number 1, all the atoms are sp2 hybridized. Now we count up pi electrons. So how many pi electrons do we have? 6. Is the lone pair on the oxygen part of the pi system? No, because we counted it as basically being part or being in a hybrid orbital. And so this one would be aromatic because it now has 6 pi electrons. This oxygen is not, it's not part of the pi system. Now I don't think I'll ask you on this exam, but in future exams when we do this, I'll ask you, I'll say, can that oxygen, is it basic? Can it accept a proton? The answer in this case is yes, it can, because that lone pair is outside of the pi system. This nitrogen, though, cannot, because its lone pair is part of the pi system. And so it has to be outside of the pi system to bond an H+. If it's part of the pi system, it's tied up, making the system aromatic. So the first nitrogen is not basic, the oxygen is. How about number 3, the square with the nitrogen? Aromatic, not aromatic, anti-aromatic. What do we think? Non? So non-aromatic because...
It's not sp2, but you can't...
Wait, stop. What was an sp2?
The nitrogen.
But it could be, couldn't it?
It could be, but if you take it and put it, like, then that would make it anti, wouldn't it?
Yes. But there's an even bigger reason why it's not aromatic.
Isn't that other bond sp3?
Yeah, it's got a CH2 group on it. The way I wrote it, I wrote it as a CH2 here, so it's definitely not aromatic because a CH2 can't be sp3. Or sorry, can't be sp2. So the way I wrote it, it's not aromatic because of the CH2. But you're right. So then what I could do is I could say this. Well, okay, let's make it sp2 by putting a plus charge. Now we didn't talk about ions, but the ions obey the same rules. An sp2, a carbocation must be sp2 hybridized. And I think I talked about that a little bit with the bridge systems, what's called Brett's rule. You can't form a carbocation on the bridgehead carbon. They showed it had to be sp2 trigonal planar. So if I did that, what would happen?
Anti because you have 4N.
Well, it would be anti, and then I would have a resonance structure that would look like this. Right, because what I would do then, and I'd give the nitrogen the plus charge. So I could have that resonance structure because I could take the pair of electrons on the nitrogen and use it to form a double bond. Either way, that molecule would be anti-aromatic. So just what does that mean? What it means is that if I made this molecule and I put a leaving group here, something that might, like a chloride, or I put a really good leaving group there, it won't leave. Even if I try and rip it out of it, if I did, I'm going to form a really unstable anti-aromatic molecule. So when we'll talk more about the ions next week. We'll just kind of mop this up, but what it means in the forming the ions is that carbocation is really unstable, and so it's going to be very difficult to form. So even if I put a leaving group there, it's going to be really difficult for me to make the leaving group leave because I'm going to form a very unstable carbocation, so likely the leaving group will not leave in that case. And you might say, but wait, that's an allylic carbocation. Sure, it is, but that's also would be an anti-aromatic one. So, triangle nitrogen. What do you think? I'll just tell you, there's multiple answers for this. Well, good to the point where when you give me an answer, I'm going to ask you why. Or I shouldn't have done that because now nobody's going to answer. But there are potential multiple answers for this.
So it wouldn't be aromatic because there's 4. Like if the nitrogen becomes sp2, then it's 4N.
Okay, so let's think about that reasoning. So if you the nitrogen, can it be sp2 or sp3? It could choose either one. So let's say it chooses to be sp2, what happens? That pair of electrons now does what? Becomes part of the pi system, which makes it 4n, 4 pi electrons, so it will not choose to be sp2. So it would have to choose to be sp3 in order to be non-aromatic.
So that's what the one above it does too, right?
Well, it didn't. This one didn't have a choice because this was already if I didn't have the positive charge there, it was already a CH2. So it is already non-aromatic.
I mean, with the positive charge.
With the positive charge, that's an interesting thing because it's going to want to form that resonance structure, which is going to then make it anti-aromatic. So in that case, it's kind of stuck. But this one, it could truly have a choice.
Wouldn't it pick a more stable resonance structure or is that not?
Remember, resonance structures are not the real thing. The real thing is the hybrid. So so even if it's a possible resonance structure, it's still going to contribute. I don't know. That's an interesting molecule. Number one, it would be really difficult to make, and I don't know if anybody's studied it. But the triangle one, so the nitrogen would have no choice but to be sp3. And so that would look like this. Here's my triangle. Sort of my sideways triangle where I have my p orbitals, and then my nitrogen would have to do this. It would have to go sp3. Normally, if you have a three-membered ring, because 3 points define a plane, remember one of the things was that an aromatic compound is planar because all the atoms are sp2 hybridized. But in this case, it would still be a planar because it's 3 atoms. It has no choice but to be a plane. But the nitrogen would deliberately not put its p orbital, would not put its pair of electrons into a p orbital. It would instead put its pair of electrons into an sp3 hybrid orbital. So that in that case, it can't be aromatic because it's not sp2. And if it becomes sp2, it becomes anti-aromatic. Well, non-aromatic is far more stable than anti-aromatic. So that's some of these questions, right? Some of these questions have multiple answers depending on how you look at them. Right? So in that case, that's the kind of reasoning we would want to think about. So there were some aromatic, anti-aromatic problems in the folder. If I ask you some, I'm just going to ask you a couple of fairly straightforward ones, I think. So just you want to take a look at it and just remember that anything with a lone pair could put its pair of electrons in the pi system, but it's only going to do that to make the system aromatic. If it isn't, it's going to stay sp3. And if it does it and it makes it anti-aromatic, it sure isn't going to do that. It's just going to stay sp3.
Can you do the withdrawing and donating groups and like the induction and resonance?
Yes.
Just like the induction?
Yes, and let me organize the table from top to bottom, which I'm not going to ask you to do, but just so we're all on the same page. So let's say I go, okay, number 1 group is an O group. Number 2 group is an N group. Okay, they both have lone pairs. Group 3 is going to be the benzene ring. So what I'm doing is I'm going from most electron donating down to number 4, which is just going to be a carbon group or an R group. So I've gone from most electron donating to least electron donating, but still electron donating. Then sort of our baseline measurement is hydrogen. So hydrogen is neither electron donating or withdrawing, right? Because hydrogen is the default group. So then once we go past hydrogen, we go to electron withdrawing. So what's our first electron withdrawing group? Halogens. Our second one is carbonyls. Our third one is C triple bond N, and our number 9 group is NO2. Okay. So going from 1 to 9, which you will not have to do, but I'm going to organize it this way because I didn't do this the other day, and I need to do it to explain the induction versus resonance. Okay, so you will have to do this on the next exam, which is a long time in the future. There's a lot of stuff between now and then, including exam number 2, right? So let's not get them out of order. And remember, exam number 2 comes before spring break, right? So don't get those 2 flip-flopped, or it'll be a bad both of those. Okay, so going from 1 to 9, this then is the most electron withdrawing. The halogen is the least electron withdrawing. Now, the reason I'm ordering it this way is because only 2 of these are induction. Okay, only 2 of these, the major reason why they're donating or withdrawing is induction. Everything else is resonance. Okay, so which ones are the 2 that are induction? The halogen and the alkyl group. So the R group and the halogen are both induction, and everything else is resonance. All of the most electron donatings are resonance. All of the electron withdrawing after halogens are resonance. Okay. Now, why am I putting it in this order? Because I'm going to reinforce the idea that resonance is far more powerful than induction by using this chart. Because if I use this chart, what does it tell me? It tells me that the groups that are in the middle, the least donating and the least withdrawing, that are on either side of the hydrogen, which is neither, are what? Induction. And once we go past the induction and we start getting more electron withdrawing on the bottom or more electron donating on the top, then it's the more powerful resonance that comes into play. Now, you could make an argument that the nitro group with the plus charge is both induction and resonance, and I think if you said both, I accepted that answer on the quiz. But really, induction is going to be just for halogens and alkyl groups, and resonance is for everything else. Okay. And so putting it in this order, that's one way to remember this order and which is which. Because I'm going to ask you to draw that. Well, yes, I'm going to ask you to draw that table again in the near future. And I'm going to ask you to put the groups in and then tell me whether they're donating, withdrawing, induction, or resonance. Okay. So on the exam, and this was not part of anybody's topics list, so I'm going to add that into my list, is number 1, electron donating and withdrawing groups. If I again give you a randomized list, could you give me, whether it's donating, withdrawing? Those should be easy points, right? So if you're flipping through going, I need to get as many points as possible, which is always the point of an exam. Use the positive approach. Don't use the negative approach if I'm trying not to miss any points, because that probably is going to happen. So if you're trying to get as many as possible, you go through, get you warmed up, and then you jump into the other problems. Or not, you can go from beginning to end. Just figure out, I'm going to start on this thing first. Right, I'm going to start on these kinds of problems first. But this will be a problem that isn't on any of the other exams. So it'll be like the quiz, but then I'll throw in one more question, which is, I'm going to do a Diels-Alder. So, give what kind of group. I want to do a Diels-Alder in the highest yield, fastest Diels-Alder reaction that I can. So which group goes where? What group goes on the diene and what kind of group goes on the alkene? Bless you. The donating group goes on the diene and the withdrawing group goes on the alkene. Correct? Correct. You should be confident in your answers. Oh, I forget. I'm on the exam and I forget. Now I've forgotten what I forgot. I forget which is which.
The way I thought about it was the two, and I was going to go from the diene and my arrows would be going out and the other one was like form 2 bond, which is losing. It would gain us a bond while the other one lost.
Yeah, I mean, the way I've drawn the arrows, that is the way you would do it. But remember, I could always draw the arrows the other way. But if it works for you, that's all that matters. I'm not going to mess with your system. Joe?
Well, just say if you forget, you can just write the same thing for both. Guarantee half.
You could do that. I guess some points is better than no points. What if we remember what we did in lab? Okay, so that's not going to help anybody. But what did we do in lab? What kind of group did we put on the double bond? We did that. I shouldn't say this either. I shouldn't say this one either, but there's going to be another Diels-Alder reaction, at least one, if not more, on the exams. And when I give them to you, I'm going to give them to you in the correct electron donating withdrawing. So if you went back and you looked at like the last quiz, one of the last quizzes that I gave you, I think I did something like this. So if you go back and look at another Diels-Alder that I've given you to write the product of, and you remember what the donating and withdrawing groups are, then the answer is right there. Because I'm not going to give you a reaction that is opposite. So if you forget, there's hopefully more than one way of doing that. One more last way is, if you think about the alkene, remember in chemistry, more stable means less reactive, more unstable means reactive, right? If you don't remember that in chemistry, remember that in people. Right? Unstable people tend to be more reactive than stable people. Not always, but the general rule. What do I want to do to make the alkene more stable? Just from the alkene perspective. Do I want to push electrons into it? That would make it more stable but less reactive. So if I'm going to make the alkene part more reactive, what do I need to do? Make it more unstable. How do I make it more unstable? Don't push electron densities into it, pull them out. Okay? So that will be one additional question along with the electron donating and withdrawing. And I'll put that in my list of topics that I'll put up today. I'll try and get them up this morning. But that's the way it is. So I'll be in over the weekend. If you have any questions, put them on Piazza, email me, come see me, and I will hopefully get your problems back to you by scan at least by noon tomorrow is my goal. Maybe today if I'm lucky.